A of t, here's V of t, and here's S of t. And we're trying to go from A of t back to S of t, right? I give you that our A of t function is a constant function, right? Negative 32. So if I graphed it, it would just be a flat line down here. Agreed? The antiderivative of this we just did a second ago, didn't we? We said the antiderivative of this was what? Negative 32t plus c, right? What does that look like? I'm just going to jot it down here. We know that V of t was negative 32t plus a constant. Isn't this a line with a negative slope, right? But it's a family of them. It's a whole family of them. So it's like, it could be that one, or that one, or that one. They're all parallel, aren't they? I don't know which one it is. I don't know which one it is. But there's one piece of information given in the problem that we didn't have before. And that's that V of 1 is 4. And that means when I plug 1 into my velocity function, I have to get 4 out, which means it has to be this one. Does that make sense? That nails down the exact curve. Yes? So we can say, this is the one. And then we go back again. Now when we go back again, we're going to have a quadratic, aren't we? And it's going to be a family of quadratics. Because I'm going to have a plus d. But I give you some information about its position. At 2, it has to be 14. So at 2, it has to be 14 up here. Then that means that it's that parabola. And now we have the exact position function. That makes sense? But we needed just 2 pieces of information. It's quite remarkable that you only need 2 pieces of information. And it's not even a lot, is it? Just give me 1 point on this graph, and I'm done. Give me 1 point on that graph, and I'm done. I've got it. Make sense? Okay. So let's do it. That was just a visual representation of what we're about to do. So find S of t. So first thing I start with is I do V of t. I like this color. V of t is, we already said, negative 32t plus c, right? But V of 1 is 4, so that implies that when I plug 1 in for t, it's going to spit out, the function will spit out 4. So this equation becomes 4 equals negative 32 times 1 plus c, right? So t is the 1, and that is the 4. And I can solve for c. So what's c here? 36? So now I know V of t. So V of t is no longer negative 32t plus some number I didn't know. It's actually negative 32t plus 36. That is my velocity function. That's a specific line on that family. And now I just do it again, right? I just go backwards one more time. Any questions? Okay, so on the next step, what would from this, and then, oh, here, I'll do this since I haven't used this. I'll use this a lot later. Have y'all ever seen the 3 dots like that in a triangle? It means therefore, okay? Therefore. In math, that symbol means therefore. So if you see me write that, I'm saying therefore. And therefore, S of t is equal to negative 16 t squared plus 36t plus, I'm going to use d again just to not confuse it with the c that we already used. But what? But S of 2 is 14, which means that 14 must equal negative 16 times 2 squared plus 36 times 2 plus d. And I can solve that for d. And on this one, again, I'm just using the fact that my 2 went in for my t's, right? And 14 is the other side of this. So that's working off this thing. Anybody get it yet? 6? D is 6? You got 22? Uh-oh. How many people get 6? Raise your hand. 6? 6? 6? Have you ever heard of a something called Fermat's last theorem? No? Fermat's last theorem? There's a very famous mathematician named Fermat, and he did a lot of really brilliant things in mathematics. And somebody was going through all his stuff after he died, and in one of his books, in just like the little margin of the book, he wrote down this conjecture, this idea that he had, and he put basically, in there he put, yeah, I can do the proof of this, but I don't have enough room in this margin to do it. And it was an open question, like we didn't know if it was right or not, because no one had proven it yet. And it's called Fermat's last theorem. And it wasn't until, I think, right in the early 2000s that it was proven finally. And when it was proven, initially, there were only about 4 people in the world who could understand the proof. It was just such a specialized proof. So my point is this, all right? Like, if 4 people in a room agree that something's right, then it's right. So if we have like 4 people say it's 6, are we good with that in here? Yeah? Like at what point are we okay with people telling us something is this? Yeah, thumbs up, right? I guess if we get enough consensus, then we'll trust it. All right, so what is it? D is what? D is 6. Okay, so do we have S of t? S of t is, we go back, it's negative 16 t squared plus 36t plus 6. Now, a question that I like to ask on a test is like this one with one change. And let me just see how this would affect you. What if I change this and instead of asking find S of t, I ask you to find S of negative 1. How would that change the problem? Yeah, you still have to do everything you just did. But at the very end now, you have the function, don't you? Yeah. So now you just plug negative 1 into it. Right? So what it's saying is, hey, look, this thing is accelerating with this function. Its velocity at 1 is 4. Its position at 2 is 14. Hey, tell me where it is at negative 1. Right? That's what this would be saying. You still have to go and recover the whole function, though. All right. Let's do another adaptation of this one. Does this help with what you were asking about? Okay. Yeah. All right. This next one is very strange initially when you see it. Not very strange. It's going to kind of throw a little bit of a wrench into things. I like that color. It doesn't erase very easy, though. How are we doing on time? 30 minutes? Good, good. Okay. So I'm going to keep that S of 2 as 14 up there. But instead of giving you that V of 1 was 4, I'm going to tell you that S of 1 is 8. S of 1 is 8. So if we go back to our 3 pictures again, acceleration, velocity, position, right? We know the acceleration function is a constant function, negative 32. We find the antiderivative, right? And it gives us a family of curves that were all these lines. Can I nail one of those down? How? This is S, though. This is S of 1, and this is S of 2. That's talking about this over here. It's not talking about V. Do you see that? I'm not giving you any conditions on this function, right? Do you see that? So you can't nail this one down, can you? Which means that if we try and go backwards again, all of these have to come back. So it's going to be like a family of families, right? So imagine like if we take that, just this one back, isn't there an entire family for that one? And if we take this one back, there's a different family for that one. And somehow we can still do it. But it seems like we couldn't with this information, but it's going to turn out we can. So do you understand fundamentally the difference between this problem and the one before it? Okay, so let's try it. We've already done the antiderivative. So v of t we know is negative 32 t plus c. We don't know what c is, and we have no information to get c. Now a of t, we can go back and get, no, not a of t, s of t. We knew that from the first problem we did. It was ct plus capital D, right? And we didn't know what c was and we didn't know what d was. So that's all we know about position right now. And I never told you what we're trying to find, right? S of t? Sorry. So in order to figure out what s and t are, or s of, what? In order for us to find out what s of t is, we actually need to figure out what c and d are, right? But we know that s of 1 is 8, right? And that tells us that when we plug 1 into this function, it's going to spit out 8. So let's do that. 8, negative 16, 1 squared plus c times 1 plus d. And if we kind of move things around here, wouldn't you get 24 is equal to c plus d? Can anybody see where we're about to go with this? What's going to wind up happening here? You're going to wind up with a system of equations. See, look, I have a result here from this first point. It gives me that, well, whatever c and d are, they need to add up to be 24. That's not enough for me to know what c and d are. But my second piece of information, and s of 2 being 14, means that when 14 comes out when you plug in 2. So let's see here. What do we get? 2 squared is 4. 4 times negative 16 is negative 64, right? And then you add that to both sides. So 64 and 14, 78. Go with me? Okay, 2c plus d, like that. So we have a system of equations. I'm going to put the big brace in front of it, college algebra, 2 equations, 2 unknowns, right? And you can solve this using one of 3 methods. You can use substitution, elimination, or a computer. Later on in this class, we will be doing systems of equations, and some of the ones that we're going to have are going to be like 5 equations, 5 unknowns, 6 equations, 6 unknowns. I think in college algebra, you at the most do 3 unknowns, 3 equations. So how many of you do not have a graphing calculator? Do not. Okay. Those of you who do, who does not have a Texas Instrument? So everybody who has a graphing calculator has a Texas Instrument, TI? Okay. Who said they don't have a graphing calculators? What's your major?
Civil engineering.
Yours? Yours? It's time. I think it's time for you. It's time for y'all to probably get a graphing calculator. Not because you absolutely have to have one, But you know, there's a lot of things in a graphing calculator that can help you down the road. I mean, just setting up tables and just can help. It's a good tool to have. All right, so if you, everyone who has the TIs, later on when we're doing the system of equations with 5 unknowns, I'm going to show you real quick on your TIs how to solve those systems with the calculators so that we can save ourselves a lot of time. All right? All right, but this one, I'm going to do this one by hand. For this one, I'm going to choose to do this system of equations using elimination. And the only reason I'm using elimination is because I see that these D's are identical. It's like D and D, right? So all I have to do is multiply this top equation by -1. And if I do that, I can add straight down. So if I multiply by -1, this becomes negative, negative, and then that becomes negative. And now if I add straight down, what do I get? 54? I think 54, right? 54 negative C plus 2C. That's just C, right? So C is 54. D's cancel. And then once I know what C is, I can go back to either one of these and get D. So I'll do 78 equals 2 times 54 plus D. I could do that, although the math there is a little more, 108. So negative 30, I believe. Someone else can confirm. It is. Okay, so our final answer is this. Our position function is negative 16 t squared plus c, but c was 54, so plus 54 t, and then plus d, but d was negative 30. So this is the answer right here. How do you feel about that? Okay? All right. That's it for this section. I want to just start talking about substitution because we still have some time. I'm going to pass around the sign-in sheet. And then I also have a sign-up sheet for the bonus for coming to my office. Now, on this sign-in sheet, I have Mondays and Wednesdays on one sheet, and Tuesdays and Thursdays on another sheet. And all you have to do is just go look at any time slot that's open that works into your schedule. If you'd like to come in and meet with me for 10, 15 minutes for the 5-point bonus on the final, right? Now, this sheet is going to start next week, and I actually am going to cut it off at the end of October. So I figure in the next 2 months, I mean, it won't do much, it won't help much if I meet you like the week before finals, right? I'd rather know a little bit more about you in the next couple of weeks. So, any questions on that? Yes.
I work on Tuesday and Thursdays because they have class until 6:45, so I don't have like.
Yeah, if you can't make any of these, you're just going to have to get with me and email, and we'll set something up. Like, I can be here on Fridays, or sometimes on these days I can make special arrangements.
I'm off tomorrow for once. I was going to come tomorrow, but I'm like, it's okay.
Yeah, we can probably work that out. Yeah. Talk to me after class. Same thing?
Yeah,
No.
is that the one we got emailed about? Because there was one,
Did you already sign up for one?
Yeah.
When is that?
10 September.
On September 10th?
Yeah.
Okay, what time?
11.
11. And that's on Monday, right? That's okay. I'm going to did anyone else sign up already? What days? Today? Okay, so that you don't need to worry about this. But if it was for next week, I need you to go ahead and fill yours out so no one else takes it. Fill yours out right here. So Monday, 11, right? Just put your name there. Make sure you write your name legibly so I can read it. And then go ahead and start passing that around. Okay, and then the sign-in sheet, I'll pass that around. And now we are going to start talking about substitution. Now, a lot of you saw the power rule. How many of you saw substitution? A little bit of substitution? All right, there you go. Hold on a second. Today's the 5th, yeah. Okay, substitution. So we're talking about antiderivatives still. This is the first of 5 techniques. Not 5 formulas, 5 techniques. We have substitution, integration by parts, trig integrals, trigonometric substitution, and partial fraction decomposition. Those are our 5 methods that we will try to employ to attack these problems. Substitution is by far the easiest, but it is also essential. Like, you cannot do everything from this point forward when it comes to antiderivatives. Everything is pyramid, right? Substitution is going to be the base. If you can't do substitution, you'll have no hope going the rest of the way. So we have to make sure we master each of these techniques before we move on to the next one, all right? All right, substitution works this way. I'm going to start this, since we only have about 19 minutes, I'm going to just try and motivate it with an example. The antiderivative of cosine of x dx. All right, what is that? Sine x plus c. All right, nothing special there, right? Nothing special. We know that. Yes? That's just one of our known ones. Now, let's do that versus that one. Your instinct may be telling you, sine 5x, right? That seem reasonable? But what's wrong with that? What's wrong with saying that the antiderivative of cosine of 5x is sine of 5x? Chain rule would cause a problem here. If we took the derivative of this, the derivative of this would be cosine of 5x, but then times 5. So this isn't correct. We actually needed out here a what? A 1/5, didn't we? And that's kind of missing. Like, how do we know that that 1/5 was there? So let me give you, so right now I'm just leaving this as a question. How about this next one? This is a good one. Can we split this up into 2 fractions? No, you have 2 terms on the bottom. You can't do that. Are you thinking arctan? Right? Because you see the 1 plus x squared? Yeah. Turns out that that's not going to do it, though. So that one's that definitely is weird, right? That one, maybe there's a way. So can you do long division? Well, you're not supposed to do long division if the power up here is smaller than the power down here. Long division is only really valid when you have a power up here that's greater than or equal to down here. So that's not going to work either. Okay, so how are we going to attack these? All I'm trying to illustrate right now is that what we have so far does not get us to this, and it doesn't have, we don't have any way of doing that, all right? So let me tell you the way substitution works. For substitution, which we're going to be calling it U sub, all right? For U sub, which is substitution, all right? For U sub, we are looking in the integrand for something and its derivative. Note, can be off by a constant. Now, just kind of ignore this. Well, I mean, don't get too bogged up on this right now, because this is weird what I just wrote up here, all right? I understand you sitting there looking at it like, what? Find something as derivative? What are you talking about? Let me illustrate, all right? We look at this problem here. I do not see that anything we've learned so far can handle this. But I'm going to look at this. I'm going to look in the integrand, and I'm going to see if I can identify two things. Something and its derivative. And it's okay if we're off by a constant. So, does anyone see something in its derivative? X squared, what's its derivative? 2x, right? Do you see a 2x? I see an x, I don't see a 2x. All right, so let me rewrite this problem a little bit so you can see how we're trying to see it. That's the same problem, right? Yes? So somebody said that they saw x here, x squared here, right? That's kind of like the something. And its derivative would be what? 2x, which we kind of have 2x here. It's x, we're off by 2, aren't we? That's what we're trying to do with substitution. See something and its derivative. Do you all follow me? You sure? Okay. Out of curiosity, could we also have picked the entire thing 1 plus x squared? What's the derivative of that? Still 2x, right? So let's try, instead of grabbing x squared, let's grab a little more. Let's grab the 1 plus x squared. So watch what I do. I'm going to make a substitution in the problem, which is why we call it substitution. The substitution that I'm going to make is that something that I saw. So I'm going to make the substitution u is equal to 1 plus x squared. All right? Bless you. Now what I'm going to do is I'm going to look at this equation, and I'm going to take the derivative of it, derivative of u, with respect to x. So the derivative of the left side, du dx, right? Derivative of this is du dx. What's the derivative of the right side? Just 2x. You with me still? Okay. Now what I'm going to do is I'm going to multiply both sides by the differential dx. Do you all agree with that? The whole idea of this substitution technique is to take this integral that we cannot solve, see something in its derivative, make a substitution, and then rewrite the integral in terms of u instead of x. Okay? I'm going to try and rewrite this in terms of u instead of x. So if I look at this, I'm going to be able to replace that entire denominator with what? With u, right? The only other thing I need to replace is x dx. I need to replace that with something, don't I? And do y'all see right here x dx? Do y'all see it? Yes? I would like to get this by itself. So what could I do to get it by itself? Divide both sides by 2. So do you agree that this is 1/2 du equals x dx? Yes? So this is almost like a match game, like you're trying to match this with something over here, and then replace this with this. So let me rewrite the whole problem. The integral becomes 1 over what? This thing, which is u, and then times 1/2 du, right? And I can look at that as being 1/2 times 1 over u du. Now, I have u's instead of x's, right? But it's the same thing now as we did before, like if these were x's. I have 1/2 times this, right? So the antiderivative of the 1/2 will come for the ride. And do you know the antiderivative of 1 over u? Natural log of u, right? Or absolute value if you want. Natural log of absolute value of u plus c. Where did the du go? It's the plus c, okay? Whatever. Understand? You sure? Now, what is u? U's this, right? U is this. So you get 1/2 natural log of 1 plus x squared. Now, I definitely don't need the absolute value. And that's because 1 plus x squared is never going to be negative. That's our answer. What? How is the antiderivative of this natural log of 1 plus x squared? Half of that. Well, let's check it. How do we check it? Take the derivative, right? So let's just ignore the half for now. What's derivative of natural log of something? 1 over it times chain rule. Derivative, what's inside? 2x. But you had the 1/2 out front. And the 1/2s cancel. The 1/2 cancels out the 2, and you're left with x over 1 plus x squared. Right? So I looked at the problem, I said, I don't know how to do that. Let me try u sub. But to use u sub, I need to see something and its derivative in here. I need to see it. If I see something in its derivative, then I can try u substitution. I'll give you another one. How about this one? Cosine x over 1 plus sine squared x dx. See, things are going to start looking pretty, like what we've done now is with u substitution, we have blown the doors open on the types of integrals we can do, like c and what we can do. Can we all agree that there's nothing that we've talked about up to this point that's going to handle that? Like the power rule, you know, it's not one of the known antiderivatives, right? I mean, we are pretty much the only thing we can turn to is u sub, right? Please understand, this is what makes Cal 2 so difficult later, is we have u sub, integration by parts, trig integrals, trigonometric substitution, partial fractions. So you get to a test, and I present you with an integral, and I don't tell you what technique to use, right? You have to just have done enough of them to be like, I see this is partial fractions, or I see this is a trigonometric substitution. Does that make sense? Right now, we know this is a u sub problem. We know it. So we know what to do, right? I mean, we know we're going to be attacking it a certain way. Does anybody see something in its derivative? 1 plus sine squared x is not quite an identity. If it was 1 minus sine squared, we'd be okay, right? Because it's sine squared x plus cosine squared x equals 1. If you move this over to the other side, it becomes 1 minus, not 1 plus. So we can't do anything with that 1 plus sine squared. I mean, you could turn sine squared into something, but asking you this question, do you see something in its derivative? Sine and cosine, right? You see that if you let u be sine, do you see its derivative there? Cosine? So I'll try and illustrate it again. If I let u be equal to sine x, the derivative of that with respect to x is cosine x. Now, what did I do last time after I did my substitution, did du dx? I moved the dx to the other side. I'm going to do that every single time. That dx is going to move over. In fact, it's going to happen so often that I'm actually not going to be writing this anymore. I'm just going to go straight to this. But for these first few examples, I'll do this. Yes?
When you do square, can you write the 1 plus sine squared?
Ah, good question. Could I actually grab the 1 this time? Could I do 1 plus sine squared? Could I have done that? Would that have been more efficient to do this? What's the derivative of this with respect to x? Well, derivative of 1 is 0, right? But this is chain rule. You would have 2 sine x, right? That's the 2 coming out. And then times derivative of sine, which is cosine x, right? That's what you would have. And this right here, see, I'm using this, you're using that for u, so the only thing you have left is this, cosine x dx, and that right there has a sine in it. So I'm glad you mentioned that because I intentionally made this 1 plus something again to see if you would want to grab more. So there's a delicate line you have to walk here. It's like you want to grab enough of it, but not too much of it. That's why you might crumble up your paper a few times. Okay, so if I do this substitution, then can I rewrite the integral right now? I mean, I think everything's ready to roll here. Cosine x dx, I've got that exactly right there. The 1 plus sine, oh no, sorry. The sine x right there I'm replacing with u. So my new integral becomes integral 1 over what? 1 plus that sine x, but it was u squared, and then the cosine x dx gets replaced with du. And do you recognize that? Arctan u. Antiderivative of that is arctangent of u plus a constant. And then we replace u. Always remember to replace u because, well, the original problem was in terms of x, so your answer better have x's in it. Make sense? You could check it, right? The derivative of arctangent of sine x would be 1 over 1 plus sine x squared times the derivative of what's in here, which is cosine x. Okay, I have 3 minutes. One more. I really like this problem. Now, before we start attacking this with u substitution, do you agree that you could expand this out, like x plus 1 times x plus 1, right? And that would give you x squared plus 2x plus 1. And then you could distribute an x through it, and then you could just do them term by term, right? We could do it with relative ease. Okay, change that to the 200th power. That way I can scare you away from that idea, right? Now, do you really want to do x plus 1 times x plus 1 times x plus 1 200 times? No. All right, so the point of me doing that is because you could initially have looked at this problem and said, oh, I'm just going to use power rule after I do a little algebra. Now I'm forcing you to not be able to do the algebra. Do you see something in its derivative? What's that? X plus 1? What's the derivative of x plus 1? 1. Do you see a 1 there? Yeah, there's ones everywhere, right? There's a 1 right there, I mean, if you want, right? So x plus 1, and just look. You all know, does anyone here play the lottery? Okay, you don't need to tell me. Look, you can't win the lottery if you don't play, right? Can't win if you don't play. You can't get through these problems if you don't try something. Right now, it does not look obvious that we have something like in the previous problem. U is sine. The derivative cosine was right there, right? The one before that, 1 plus x squared. The derivative 2x. It was kind of up there. Here, x plus 1, the derivative is 1, yeah, but does that even help? I don't know. You got to play. Let's try it. Because I know I don't want to expand that out 200 times. So let's try that. If I do that, then I'm going to have du dx equals 1, which is really du is equal to dx. That fair for me to just do that?
Yep.
Okay. So I'm going to be able to rewrite this. Do you agree this right here, check, I've got that. Yes, that's going to be du? And do you agree that this x plus 1 I'm going to be able to replace with u? Yes? But what about that x out front? Why don't we take this equation here, because that's a relationship that we have between u and x, isn't it? And can't I replace that? Let's see, if I solve this for x, don't I get x is equal to u minus 1? Do y'all see that? Okay, let's rewrite the problem, because now I know what to replace x with. So if I rewrite this integral, it becomes x, which you said was what? U minus 1. I need to put that in parentheses. U minus 1. And then times, what was x plus 1? U to what power? 200. Shoot, I still have the 200 there. Dx is actually du. So you look at that, and maybe initially you're like, crap, that didn't help. But it did. Because u to the 200th, I can just distribute that through this parentheses. Right? Here, I could not distribute the x through because you have to do the 200th power first. Here, we've kind of very strangely made it doable. Yeah, it's like we reversed them. And so now when we integrate, or not integrate, when we distribute, you get u to the 200th minus 201. U to the 201 minus u to the 200 du. And we've got separate terms now, separated with subtraction. I'm over on time, sorry. But the antiderivative of this would be 1 over 202 u to the 202 minus 1 over 201 u to the 201. And then replace u with x plus 1. So I hope that this real quick glimpse into substitution, which we'll do entirely on Monday, that's all we're going to do is substitution. I hope that this gives you a glimpse into the kind of different game we now get to play. All right? It's not as straightforward anymore. Make sure you do all your homework for 4.7 antiderivatives. And you're free to start this if you'd like. The first few problems out of this section actually give you an integral, and they actually tell you what you should use for the substitution. So you might want to just do those first few. Okay, have a good weekend. That's it, right? One day we're one and done, huh? I did pass around a stack of homework. Where is it at? Is the stack gone around to everyone? Is it over here?
Yeah, I think
Yes.
a couple people came in late.
Yep, let me turn off my camera. That's all I have. Thank you. Turn this off real quick.